Hello everyone, welcome to today's introductory lecture on educational analytics, and we are considering the aspects of reliability estimations. Now, when you are to carry out some form of data analysis or some form of pre-data processing, you are going to ensure the credibility of the data sets. Now, we always ask the question, do we really believe that your data is going to measure the intended outcome, or do we believe that the constructs that you have selected from maybe a pool of constructs, do they really represent the sample frame of that particular construct? So all these questions is what the reliability estimation can help you to answer. Also, the reliability estimation help us to determine the dependability of our results, and also establishes the confidence that we have in your analytical tools. So for instance, if you have two or more raters or validators trying to validate a particular analytical tool, maybe a measuring instrument, maybe could be a questionnaire, it could be an achievement test. Because you have different raters, now the notion of human subjective judgment can come into play. So how can we use our empirical techniques to establish that your data is going to measure the intended outcome or the intended constructs or concepts consistently and over time? So we have that the reliability of an instrument is practically an umbrella term that enables us to determine if the instrument is appropriate, if the instrument is stable in terms of the content, if it is stable in terms of the time frame to be used, if it is stable for a particular group of the students. Invariably, we are trying to establish the heterogeneity of each of the items. If you have different items to measure a particular construct, do they measure that construct distinctively, or are the items mutually exclusive to elicit the responses from the test takers or the testees, as the case may be? So that is what reliability help you to answer. We have different types of reliability estimations, and the very simple one that we consider is the test-retest reliability. Test So in test-retest reliability, as the name implies, you are going to select your possible test items or question from a particular content or a particular concept, and then you administer the test to the testees twice. So that means you are going to administer it maybe within a particular time frame. You assign a particular time frame for the test. You administer the test the first time, and then you administer the test the second time. Thereafter, you will correlate the scores. You can use the Pearson product moment correlation coefficient to establish the correlation coefficients, or you can use the Spearman rank correlation coefficients. So for instance, if we are given a set of data, say this is the first set of data that you obtain after the first test. These are the set of data x1, x2, x3 to xn, and in the second test, this is the same. This is another set of data that you obtain. So you are to correlate these two sets of data, possibly using the PPMC, which I've mentioned before. The PPMC, that is Pearson product moment correlation coefficient. So you now proceed to do that. The simple reliability estimate of this data set is expressed in this equation as n summation xy minus summation x summation y divided by the square root of n summation x squared minus summation x all squared, close it, and n summation y squared minus summation y all squared, and you close it. Remember, the square root sign takes care of the entire denominator. So this is the expression that you use to compute the reliability index in a test with test reliability computation. So, but the issue that always bother us is on the interval, the time interval that you're going to choose or select, so that you will reduce some redundancy effect. Example, the crossover effect, maybe memory effect, maybe because they have taken the test before, so there's a possibility that they can easily recall the answer to the next test, because the items are not varied. The items are not varied. You only vary the time frame of giving the test. So some professionals say it could be 1 week, some say it could be 2 weeks, but there's no specific time frame to give the retest. But this is the expression that you use. It's a familiar equation that establishes a kind of a casual relationship between two variables of interest. So based on some comments, we are going to take an example of how to compute the reliability index using the test with test technique. So this is the array of data sets that we are going to use. For instance, we have we give the first test, and this is test 1, and this is test 2. Then we have the number of test takers, or the study participants, number of testees. Here, serial number 1, 2, 5, 6. So we have 5. We just take a very small sample in this case. But note, in practicality, in practical sense, you must always have a large sample size, because that is in conformity to the general classical test theory. Because the larger the test item, the more reliable the test instruments will be. So in practice, you should always have a large sample of the test items, as well as a large sample of the test participants. So we had given this table 5, 5, 5, 6, 6, 6, 6, 7, 7, 6. So from here, we can denote this to be the x and this one to be y. These are just mere parameters that we'll use so that it will simplify the process for us. So the next step, if you want to follow the formula, is you need to compute the product, that is xy, compute the square of x, and then compute the square of y squared. So this will be If you do that arithmetic, you have 25, 25, 36, 36, 42. Next one is 25, 36, 36, 42, and 36. That means you square the corresponding column of the x and y variables, and you have that. This is x squared, and this is y squared. So here you are going to have their products. You are going to have their products, x, y. So their products will be, this is 25, 30, 66, 36, 7, 42, and here you also have 42. So the next thing is for you to get the average of each of the rows. So get this average. That will be 29, 30, have 172, 182, and 175. So those are arithmetical issues, and then you are going to plug in the averages. Let's say this is the average. So here we are going to say average of x. Here is average of y. Here is average of x squared. Here is average of y squared, and here is average of xy. Now you could see that these are the parameters that we have identified in the formula we listed before. So you now plug in these parameters into that formula. Obviously, you can denote the r to be equals to n in this case, which is the number of sample size, that is number of participants, n multiplied by the summation xy based on the formula that we gave to you. So you have 29 by 30, and you divide it by the square root of 5 times, this is x squared 172 minus the x 29 squared, close the bracket. Remember, square root sign covers the second bracket as well. So this y, now 5 times 182 minus the product of y squared, you have 30 squared. So after your computation, you arrive at 0.45. So this is the reliability index of this particular instrument. Obviously, it is very low. So if you are going to compare it to the conventional practice, obviously we say that the closer the reliability index is to 1, the better it is. So if it is at least 0.7 to 0.9, you could say that your instrument is reliable. But there is a specific scale that you can use to match it with this reliability index. So for this computation, we have a 0.45. Note that it must always be a positive number that lies between 0 and 1, because we want to establish a positive relationship that does not show any significant variation in the number of in the test interval. So if the test instrument maintain the stability over time, I think that is another definition of reliability, maintaining stability over time. So the instrument is stable at subsequent time, but you are going to assign it to the same set of testes, So this is the reliability index, and that is a very simple one that that you can use to establish your reliability index. But like I told you before, it could have some challenges because there's going to be a possible measurement error in terms of the sample, the content sampling error. So that is the problem. Maybe you are unable to select a true representation of items based on the contents that the test instrument is supposed to measure. So there's that possibility of having a content sampling error, as well as maybe the timing error, because the timing error is also one of the factors. It's also one of the factors in the sense that there could be some environmental factors that could affect the testee at a particular time, or where the test is taking place, the environment where the test is taking place, as well as personal factors. So that is the simple way that we can compute using test with test technique. Now the next one is equivalent form reliability. Equivalent form reliability. You may not see this below, but the index RAB is 0.45. So you should be able to do the computation using the formula, because it's simple, just a 5-point data pay, and with this you could arrive at that. So the next one is called equivalence form reliability. 2. Now, because of the challenges that we have in the test with test technique, they now decide to come up with the equivalence form reliability, because in that test with test, it has the problem of the carryover effects or memory effects and other challenges, because they don't reselect they don't randomize the items. So in this case, you are going to create two forms of tests. You are going to create two forms of tests, maybe, but they are going to be equivalent and parallel. They are going to be equivalent and parallel. Equivalent in the sense that you could randomly select question maybe from a pool of questions that you have that is supposed to measure a particular concept of interest. You are going to randomly select the question, and then because they are to measure the same concept, we believe that it's going to be a true representation of the contents, but different forms, in the sense that they will represent the contents, they will represent the constructs effectively. And I think that you could check that using the validator's index. So select a possible question that are of equivalence, like two sets of questions that are equivalent in the sense of the contents as well as the constructs. So you are now going to assign, you are now going to issue out the instrument or administer the instrument to the respondents, possibly simultaneously. Maybe you administer at the first time, and without wasting more time, you then administer the second one. That means like a back to back. You assign it, you administer it back to back to the respondents. So this one takes consideration of that effect of item contents error, because you are now trying to reshuffle it. For instance, you want to do maybe tests, post tests, they say pre-tests and post tests. This is a typical example of equivalence form reliability check. So you give a pre-test, Then in the post-test, you can possibly reshuffle the items, or you can randomize the item as well. And also note that there is one issue regarding this equivalent form that people really neglect. It is also possible for you to randomly select the test participants. So it is possible for you to give the first test to a particular group and then give the equivalence form to a particular group. But the only thing is that the two test groups must come from the same sample frame. They must come from the same sample frame. So once you are able to do that, you then proceed to compute the reliability coefficients, possibly using maybe correlation coefficients or Mann-Whitney U-test, as the case may be. Or you can even use Spearman rank. You can also use Spearman rank to carry out the computation. So it is similar to what we did before, but it is the only difference is that the test is of different forms and it could be given to different groups of testes. Yes. So the same formula can also be applied. The same formula can also be applied to compute the reliability index. But all the same, it may not really reduce that redundancy in the process. But there's what they call delayed administration. You can do a delayed administration. It's also a way to reduce that redundancy if you do a delayed administration. Maybe after some time you now give the test. But the equivalence form, that means the two test groups have different set of questions, but they are equivalent because we believe that they are heterogeneous. So each of the items will measure a particular intending construct distinctively, and also they are independent of the other, or you say that they are mutually exclusive. So that is the second form of reliability estimation. Then what will also help you to guarantee reliability in equivalent form is that the mean of x should almost be the same as the mean value of y, as well as maybe their standard deviation should almost be the same. Their standard deviation should almost be the same, as well as the standard error of the measurement. For instance, you can decide to compute the standard error of the measurements of each of the test groups by multiplying the standard deviation by 1 minus the correlation coefficient of AB. So the smaller the standard error, the more reliable the instrument is. So that is a different case or a different form of reliability check for your analytical tools. Example, in the case of maybe a measuring instrument like questionnaire or performance test items. Now the next group is the internal consistency, reliability index for internal consistency. So you have internal consistency reliability. Now, because of the challenges or issues in the previous two reliability computation, in which they don't really measure the internal consistency of the instruments or of the test items, because the test is being considered to be stable over time, so they don't consider the stability within the test items in a particular measuring instrument. So the stability within a test item in a particular measuring instrument is what we call the measure of the internal consistency of the instrument. So there are different ways you can compute the reliability index to ensure or ascertain the internal consistency of the instrument. Now, the very important point that you should note is that regarding the notion of internal consistency, we are trying to ensure that we put the difficulty indices of the respondents into consideration, or difficulty indices of the test items into consideration, because if we have variations in the difficulty index, it's going to affect the reliability of the instrument. So it is sensitive to the heterogeneity of the items. A very important idea is that internal consistency is sensitive to the heterogeneity of the test items. So any variation in the difficulty index of each of the items is going to affect the test results, or is going to affect the reliability of that instrument. So one of the ways that we use to compute or ensure internal consistency of the instrument is the split half reliability, or split half technique. Split half reliability. Now, in this case, in split half reliability, we are giving the test, or we administer the test just once for a particular group of testees, and then we can randomly assign the test scores into two groups, maybe using a simple technique like dividing it into odd and even group. So you split the results that you obtain from a particular test into two halves, and then proceed to compute the reliability index. It could be possible to use the correlation coefficient by PPMC, or the Spearman rank correlation coefficient. Now, because of the idea that we have gotten from the general theory of tests, or the classical test theory, the smaller the sample, the larger the smaller the reliability, because once you divide the items or the item results into two halves, you are reducing the sample point that you are going to use for the computation. So we then proceed to apply what they call the Spearman-Brown's privacy formula. You have the Spearman-Brown privacy formula. So the Spearman-Brown formula is defined as 2R over 1 plus R. Or you can remove this half here. Just define it as 2R divided by 1 plus R. Now, where this R is the correlation coefficients. The R is the correlation coefficient in this case. So it is just a correction factor of the correlation coefficient. So typically, how do you do that? If you divide the test items or the test scores into two groups, possibly by randomization or using odd and even numbers to separate them into groups, you are going to use correlation coefficient, maybe the PPMC, to obtain this R. This is the correlation coefficient. So once you obtain this R, remember the test is only given just once. Once you obtain this R, you now plug it into this formula. Now let us consider the previous example that we had, because we had the reliability index to be 0.45. So if after splitting, we are now making the assumption that, okay, we have given a test to a particular number of students, say 10 students, 10 students who are part of the sample frame, or they could also be part of the targeted population, as the case may be, because you may not actually use this particular group of students in the actual experiment. In the actual experiment, because of some confounding effects that could affect the results. So they are also part of the sample frame, but you are not going to use them for the actual experiment. They are just for empirical purpose. Then you are going to plug in. Remember, we had R to be 0.45. After splitting, you obtain the correlation coefficient to be 0.45 and you plug it in. It's just a multiple. So to perform that arithmetic, you have 2 by 0.45 divided by 1 plus 0.45, and that gives you 0.62. So the prophecy in this case the prophecy in this case is that it will always increase the reliability index. It will always increase the reliability index. I think this man was a prophet, because he cited one Bible portion in the process and say we should go and read Jeremiah 19:7, that the human heart is subjective in its judgment. So he does not believe somebody. You have to prove using some form of empirical techniques like this for the person to be sure that your data is reliable. So that is the technique concerning split half reliability index. You split them into two and then complete the reliability. We should look at possible errors in it, which we have already highlighted for you. That one of the errors is that it's going to reduce the sample frame, and that will affect the internal consistency of the test items. But this is an improvement. Is an improvement in the reliability index, because it's going to increase the reliability index and also measures the internal consistency of the items. So although there could be measurement error, for instance, maybe content sample error in the process, but you will not have that error as a result of time, schedule, as the case may be. So no extraneous factor regarding shift in time, because in this case the test is only given just once. It's only administered once to the participants or the testees. Now the next one concerning internal reliability is the Kuda-Richardson 20. We have the Kuda-Richardson 20 as another way to compute the reliability index that can enable us to ensure internal consistency. We call it Kuda-Richardson reliability. Kuda-Richardson reliability. Some people call it KR. There are two forms. We have Kuda-Richardson 20 and Kuda-Richardson 21. So if you want to consider the first one, Kuda-Richardson 20, the name depends on the difficulty index conditions. So in Kuda-Richardson 20, the assumption is that each of the test items has variations in the difficulty index. So KR20 is defined as K over K minus 1 into 1 minus summation Pi Qi over the variance of the test instruments. If it runs from 1 to n, so I can 1 here to n. N is the number of items. Now K is the number of items in this case. See, it's also equals to K. Let us put it as K. K is the number of items. It runs from 0 to K. This is 0. This is 1 to k. So k is the number of items. Now you have to define the parameters clearly. The pi is the same as the proportion of students that answers the question correctly, or the proportions of items that we answered correctly. That's how we define p. Proportion of items answered correctly, and qi is proportion of items answered wrongly. We always see this kind of scenario in maybe a binomial expansion. So we now say that this one is 1 minus pi. I runs from 1 to k. Then here, this is the variance of the item, the variance of the test items, the variance of some of the test items. So this is the expression that we use to compute the reliability index that will ensure internal consistency if we are to follow the KR20. Now you can make use of the KR20 when the test items are scored dichotomously. So this is a typical condition that we must follow. If the tests are scored dichotomously, so that means it could be a yes or no answer, or it could be 0 or 1 answer. But for instance, the multiple choice question, because the multiple choice question is either you are correct or you are wrong. It's either you are correct or you are wrong. So it is being scored dichotomously. So if the test items are scored dichotomously, you are going to use KR20, and with the assumption that each of the items have variations in their difficulty indices. So let us take an example, because that is one of the comments that they gave to me in a previous lecture, that we should cite the example. But I think because of time, we always take that to our real class. But let us see how we can give you some fictitious data that can enable us to explain this particular concept of reliability. So if you have item 1, item 2, item 3, item 4, and let us say item 5. And this was taken by some students, some 6 students. You can say student 1, student 2, student 3, student 4, student 5, and student 6. These are the number of the testees, as the case may be. So we have scores for them. You have, maybe this one got it right. This one got it wrong here, but got it right here and right. Wrong, right, wrong, and right. Right, wrong, right, wrong. You can have right, wrong, right. We have right, wrong, and right, and right here. So with that, you can obtain the total score here. You sum them. Is 1, 2, 3, 4. So you have 4. Follow that sequence. 4, 5, 2, 1, 5, 4. So that is the total score of the test items for a particular student. Now the next thing you should compute is the proportions. The proportion of correct answer also is the difficulty That's also the difficulty index. So you can say this is Pi. The proportion of correct answer is add all the correct answers and divide by the total number of questions. If you do that, you have 0.82. If you do that here, you have 1, 2, 3. 3 divided by 6 is 0.2. That is half. And then you follow that train, you have 0.67. Have 0.83. 0.67 again, and you have a yes, that's the end, because this is the total score of the test item per students. Then you can compute the other one, which is the proportion of students that scored proportion of items scored wrongly or answered the correct wrongly. Is so it's just a reverse of this one. Remember, we say that Pi, we say that the Qi is the same thing as 1 minus Pi. So by that, you use that procedure. You have 0.16, and then you follow that train, you get there. Then remember to plug it into the KR20. We have defined the KR20 before, so you've seen that the total number of items in this case, which is K, is 5 items. So you have 5 divided by 4 into 1 minus the summation of these products. Remember, you are going to multiply Pi and Qi and get the products, and the summation of that product. The summation of that product is 0.96. That is what you 0.97. That is what you plug in here. Sorry, 0.97, and then you divide by the variance. Variance is 2.25. It's simple for you to obtain the variance of a test score, because we consider it to be discrete set of data. So we now say you can apply n summation x squared minus summation x all squared divided by n into n minus 1, or you divide it by just n, depending on the estimation index you are going to use. So when you plug it in and you simplify, you arrive at 0.71. So 0.71 as a reliability index is acceptable, because we say that there is a positive relationship, a strong positive relationship, but not very strong or perfect, but a strong positive relationship. So the items have different difficulty indices. So that is what you follow when you want to apply the KR20. So that's one of the simple questions that we used to ask the undergraduate students. Why did you use KR20, and why did you use KR21? The difference is that for KR20, we assume that the difficulty index varies, but in KR21, which we are going to show you, we don't consider that variation in items. So we only use the mean value of the items. So we have KR21. The KR21 is similar to KR20, but the assumption here is that all the items have equal difficulty indices. All of the items have equal difficulty indices. So we express it as K divided by K minus 1, K being the number of items, 1 minus the mean, that is the average of the responses per student, average of the responses across all the students, 1 K minus that same mean again, divided by the K value times the standard deviation, the variance of the test item. You close the bracket. The parameters have been defined as I writing the formula. K is the number of items and M is the mean responses of all the testees or respondents, and then sigma squared x is the variance of responses of all the testees. I don't think that you can see that very well. Let me redo it. So this is the mean of test responses, and this is the variance of test responses. So that is the simple formula that we use to compute the reliability index to ensure internal consistency regarding KR21. The assumption is that there's equality in the items, there's equal difficulty index in the items. So we only make use of the mean of the items. So if you look back in that data, it is possible for you to obtain the mean of the total scores. So that is the only parameter that will change. That's the only parameter that will change in this case. So the mean of the total responses of the students, if you compute it, you have 3.5. You have 3.5. Remember, we know the number of items to be 6, and then we know the variance to be 2.25. 2.25. Variance 2.25. So if you plug it into this formula, you will be able to obtain a reliability index of maybe 0.43. Now, once you obtain this one, it quickly reminds you that this is an underestimation. This is an underestimation of the reliability index because it is always smaller than KR20. So conventionally KR21 or KR20 is always greater than or equals to KR21. So it gives an underestimation of the reliability index. I think that is one of the challenge that we have when we are using KR21. So sometimes we say don't use the KR21 because it does not give us a better estimation, rather it only approximates the reliability index, in the sense that it gives us a lower, it's underfits, like underestimates. It underestimates the reliability computation. So those are the aspects of internal consistency. But we have the general form. Obviously, for those that were asking us to use SPSS to do analytics because it's 21st century, it is also necessary for you to learn the theoretical aspect, because this is how we build the SPSS platform. These are the computations. So you could also learn from the roots, so that when we go to maybe using those SPSS statistical packages or any form of application softwares to compute it, maybe basically for flexibility, you will be able to appreciate why we do so and how we obtain it. Now, the next one is the Grunberg alpha. We call it Grunberg's alpha index. Grunberg's alpha index or reliability coefficients. It's very well. The Grunberg's alpha index. Now, the Grunberg alpha reliability coefficient is is a general form of both the Kuda-Richardson 20 and Kuda-Richardson 21. So it is used to obtain the reliability index for instruments that are scored not just only dichotomous, but instruments that are also scored polytomously. Instruments that are scored polytomously. So that means this one is for maybe multiple choice questions. Multiple choice questions, and this could be for maybe Likert scale kind of Likert scale items, because here you only have yes or no answer, but here you have multiple answers. So for multiple answers of a particular item in your test instrument, you should use the Gunbach Alpha Reliability Index, and it always works for if you have a large sample size to be used for computation of the reliability index. We have the alpha coefficient denoted as C alpha. This one is a matter of nomenclature, whatever notation you want to use, provided you will understand what it means, you use it. So you have K divided by K minus 1 into 1 minus, here you are going to sum the variances of each of the test item. You could see I equals to 1 to K in this case. And then you divide by the variance of the entire tests. So that is just the difference. Here you will proceed to compute the variances of each of the test item. This is just the additional parameter from the previous one, the additional parameter there. So we have to take example. That is let us take an example to see how we can apply the Gunbach alpha. I've told you this one is general form. It is also sensitive. The Gunbach alpha is also sensitive to the heterogeneity of the test items. So he's going to consider that, and then this is an example. So by heterogeneity of the test item, we mean that even though the items measures a particular construct distinctively, we are going to have a reliable index. So if you have item 1, item 2, item 3, item 4, item 5, and then you have the total here. Maybe these are the respondents or the number of participants, as the case may be. You have student 1, student 1, student 2, student 3, student 4, student 5. Now, these are fictitious data sets that we only frame for example, or for practical purpose. But in real scenario, you will have a large sample size that gives you a true representation of your targeted population. So we have, maybe we consider a Likert scale that was scored using 4 coding, say strongly agree to be 4 points, agree 3 points, disagree 2 points, strongly disagree 1 point. Now let me use this opportunity to correct one misconception about this Likert scale. You will see that in some research work, they will add one particular coding here, say neutral. We don't expect to see that neutral because it improves, it inflates the scores. It may inflate the scores and then invariably reduce the reliability index, because a decision that is neutral should not necessarily be between agree and disagree. Yes, it should not necessarily be agree and disagree, because it's going to affect the coding, unless you want to say 3.5, but that is not necessary, because the Likert scale is not categorized as a continuous scale. is not categorized as a continuous scale. It is categorized as categorical variable. Categorical variable. It is not a continuous variable. So if you put 2.5 there, at the coding stage, it is likely going to inflate the score and then gives you some form of estimation bias and error, unless maybe after the pre-analytics or in the process you conduct some form of a data transformation, possibly maybe the mean or the log transformation as the case may be, to convert it to a continuous scale. But that is not the bone of contention for today. Let's now fix the data points. 43242. Okay, you have six participants. Sorry, it was 6 participants or 6 testees. Maybe this was a questionnaire given to students to assess the performance of online students that learn via application softwares or using any other flexible learning tool, as well as those ones that learn the same concept in the real-time classroom. If you make the assumption, it's interesting. You proceed 3, 3, 3, 3. Say 3 and 2. This is 4. 3, 3, 3. Okay, 4, 3, 2. Then we proceed 4, 2, 2, 5, 4, 2. 5, 3, 2, 3, 2, 1. We have 5, 3, 1, 4, 3, 3. So these are data sets that maybe could be seen as the responses of 6 students on their level of agreement regarding the online tutorials. So they give you this response. So you can obtain the total. Simple arithmetic, add all this: 21, 14, 10, 20, 14, and 10. So that is the sum. With that, this total, this is the total score per student. So you can obtain the variance. Of the test score. Overall variance of the test score to be 18.81. 18.81. And then you proceed to obtain the variances of each of the test items. That is why I now link it from 1 to k. K being the number of the test item. So get the variance of this one. You know the simple formula that we can use to obtain the variance. I've written it before. So this is n, x squared minus summation x over n into n minus 1. So this is a variance. If you take square root, it becomes a standard deviation. This is for discrete data set. So if you do that, you are going to obtain 0.81, 0.33, 1.47, 1.55, and 1.47. So these are the variances of each of the items. You could see this one is very sensitive to the difficulty indices of each of the test items, or the variations in the test items based on the number of the respondents. So you can proceed to plug in into Cronbach alpha equals to the number of items is 5 minus 1, so you have 4 here because you subtract it by 1, and then 1 minus the summation of the variances of each of the test items. So you now sum these ones. So just say plus, 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 plus. Carry that result and fix as the, let me just write it for you, 0.81 plus 2 plus 1.47. You divide it by the variance of the entire test items. So you then proceed to obtain the reliability at 0.8 0.87. So this is the reliability index for this particular fictitious data set. So if you have this kind of index, you can say, okay, that instrument is valid enough. It's valid enough based on the conventional interpretation that if you have 0.87, you can assume a very strong positive relationship. So this is good enough. That means you can use that instrument. You can use that instrument to conduct your real data analysis, because these are basics which we consider in pre-analytic tools. You consider this as one of the pre-things that you're going to do before you use the instruments for data analysis. Now, if you want to follow the CCMAS, the CCMAS has now been able to change some of the conceptions that we had before concerning reliability. Initially, we classified inter-rater reliability. We said the next one, the new CCMAS. If you want to follow the new CCMAS curriculum, you see that CCMAS. You see that inter-rater reliability is no longer classified as reliability. It is classified under validation estimations. So we will not consider inter-rater reliability as a type of reliability. Rather, we are going to consider it as a type of validation instrument. So, for instance, you want to validate, or you want to see the extent of the agreement between two or more validators of a particular instrument. Maybe there's a ranking that you have given, that they should rank the instrument from 1 to 5. Now, those validators will give you the scores based on each of the instruments after assessing possibly the construct itself, the contents itself, the framing of the questions, and the formatting or the structural arrangement of the items. That is where knowledge of the experts, expert knowledge is required for validation. So you give your instrument to experts to give you a validation index. Now we are concerned with also not just the reliability index. Note, if you want to follow the CCMAS assessment, we are also going to consider the validators index. Before, initially, we only conduct empirical analytics for the reliability of the instruments, but we neglect the validators index. Example, the coefficient of concordance. So the validators index is coming to play, which will enable you to see the extent of agreements between two or more validators on a given analytical tools. Example, a questionnaire or achievement test. So validity also have indices, which I've mentioned to you. Maybe we have other ones like, is it Kendall's? Have Kendall's as well. We have the coefficient of concordance, and the other ways to establish the validity of an instrument, and it has an index as well. So it is now empirical. It has some empirical connotation in the CCMAS, because you need to give us the value of the validators, the validators index. I think that is going to be considered much more explicitly in a different class. So in our subsequent lectures, we are going to consider the validation of instrument or validity indices. So if you have any question or any observation, you can put it in the comment section. But please remember to follow us in our YouTube channels, EdTech Analytics, and follow us on Facebook at Analytics. Thank you so much for listening.